Welcome to another EE301 lecture. Today we'll be talking about series and parallel circuits with a heavy dose of problem solving. So we'll jump right into this with an example of a hybrid series and parallel circuit as we step through some of the basic procedures for how we go about tackling this sort of problem. So you'll notice here that we have 5 resistors, some in series and some in parallel. In order to be able to find the total resistance, there's going to be several steps involved. First, we'll note that these 2 resistors are in series with one another. So we can have an R equivalent for those 2. Second thing you'll notice is that those 2 resistors are also in parallel with this resistor, R2. So we'll have an R equivalent for those. Then you'll notice that this resistor is in series with the combination of those 3 and with R5. So we have a third R equivalent. So we can effectively redraw this to have R1 R2, and our new R equivalent here, which is R3 plus R4, and then of course R5. We can redraw this again and have again R1, and then a new R equivalent here, and R5, where this R equivalent is R2 in parallel with R3 and R4, and this is R5. And then finally, we can redraw this whole circuit to be one element with the 3 of those in parallel, which we write as R total is equal to R1 plus R2 in parallel with R3 plus R4 plus R5. Seems complicated, but you do this a few times, it becomes pretty easy. Here's a quick example. So in this case, we have R1, which is in parallel with the combination of R2, R3, and R4. R2 is in series with R3 and R4, and R3 and R4 are in parallel with one another. So we have parallel, series, parallel. We write this out as R total is equal to R1 is in parallel with R2, which is in series with R3 in parallel with R4. If we're given values for each of these, we say R1 is equal to 10 ohms, R2 is 15 ohms, R3 is 50 ohms, and R4 is also 50 ohms. Then we can plug in values here, being careful to keep in mind order of operations. 10 is in parallel with 15 plus R3 and R4 in parallel. Since they are equivalent values, they're both 50, the total resistance of those 2 in parallel is just 50 divided by 2. And again, we maintain our units here in ohms. This becomes 1 over 10 plus 1 over 40. 40 came from just the sum of these 2 values. That's in ohms, and this comes out to 8 ohms. Another example. In this case, we note that we have R3 and R4 although they are perpendicular to one another, they're in series, because the current which passes through R3 is the same current which passes through R4. So those we put in series with one another. R3 plus R4. We note that R3 and R4, that combination, is in parallel with R2. And then we note that this entire quantity is in series with R1, because the total current which flows through this flows through this entire mess. And that is just going to be our R total. We plug in extra values here. We get R total is equal to 2.5 plus 1 over 10 plus 1 over 25 plus 5 to the negative 1, and that's in ohms. Our total comes out to 10 ohms. If we're trying to solve for I total, we just use Ohm's law. We know V total, given to us in the problem. And we now know R total, because we just solved for it. We get 24 volts over 10 ohms to give 2.4 amps. If we wanted to solve for any individual current, for example, I1, we're simply going to use our current divider rule. We take our 2.4 amps for I total, multiply that by the equivalent resistance that we care about, divided by the branch that we care about. Now, you'll notice here, this value is not the same as this value, despite the fact that our equation for our current divider rule is that I1 is equal to I total times R total over R1. The reason for that is because these are two different R totals. This is R total for the entire circuit. This is R total to the relevant part of the circuit for the current divider rule. By that, what I mean is the current that we care about, that we're trying to solve for, I1, is here. Which means the current that we're dividing using our current divider rule is coming in here. That current has already passed through this resistor. Therefore, that resistor is entirely irrelevant to our equation. So the R total that we're using with our current divider rule is only the combination of R2, R3, and R4. Because R1, that current that's being divided at node A, that current has already passed through R1. So it is irrelevant to the actual division that we care about. So mathematical sum here, 1.8 amps. Now let's say we're trying to solve for I2. If we're trying to solve for I2, well, we already know I1, and we know that our total is going to be still 2.4 amps. So we just take our total current minus the current down the branch we solve for to get whatever's left over. If we know we have 2.4 amps coming in and we have 1.8 amps going down here, then whatever's left going down this branch must be the difference between those two values. And that's simply 600 milliamps. We've sort of used the KCL, the Kirchhoff's current law, in disguise to solve for this one. we'll talk a little bit about some problem-solving techniques. There's a basic structure that you should try to follow in solving these problems, especially if you're a little bit lost. To one, get points in the absence of having a clear path forward, and also to help you to I guess, figure out what path you should take just by following a basic rubric. Step one is going to be to redraw the circuit. What you want is to have a circuit that has your voltage source on the side, and then everything else, resistors, etc., all that downstream on the right side. Make it look like something you're used to. Step two is strategize. Look at what you're being asked to find. Recognize what values you need to solve for to get there. Determine what laws are going to be applicable, what equations on your equation sheet you may want to use. Come up with a plan instead of blindly charging forward. Step three is to find your equivalent resistances and simplify your circuit. If you start off with a whole bunch of gobbledygook, you'll find things are much easier to solve for if it's easier on the eyes. So simplifying your circuit, if you have 10 elements in series, make it one simple R equivalent, and things will become easier to strategize. Step four, find R total. You're going to need R total in order to solve for the next step, which is to find I total. Typically, problems involving lots of resistors in series and parallel with these sort of circuit analyses, it's going to be important to solve for I total. Even if you're not explicitly told to find it, frequently that's required to find the thing you are asked to find. Step six, label component polarities. What I mean by that, again, is if you have a resistor, for example, and you know you have current going this direction, your polarity, because current causes a voltage to drop across your resistor, is going to go from positive to negative. And that's helpful for identifying your voltages in the direction of them when doing loop analysis later on. Step seven is going to be to calculate. So find whatever you're asked to find. Step eight is going to be your dummy check. One of the things you should be taking away from this class is a gut understanding of should this value be higher or lower than this one. So dummy check yourself, ask yourself if it makes sense. Should you be getting a negative there? Should you be getting a positive? Step nine, make sure you have the appropriate units. Step 10, engineering notation. Make sure those units correspond to the appropriate engineering notation for the answer.